Oh, Haley. Hello, Hadassah. Yeah, nice seeing you connected. Just a little second to bring up the slides and maybe to wait a few more people to join. Hadassah, which course do you teach? What do you TA?
I'm TAing the physics 120L lab, which is the general lab, and 2 of the 251L labs, which are the class X mechanics, calculus-based lab courses.
Okay, I see. So both labs that you are teaching are like mechanics.
Yeah.
I see. Is there any component of fun in this, or it is only like a waste of time and hard work?
I think for me, it's fun teaching labs and just doing some of the concepts. Since I don't have to worry about being graded, but it helps. It helps me to. Some of the labs I've seen similar labs in my undergraduate, and now these labs make much more sense now that I'm doing them later. So
Okay.
it's fun to revisit.
So you take it as an educational benefit for yourself for a little revision.
Yeah, and I enjoy teaching the labs too. So
okay. Hello, Mara. Nice seeing you connected. Let's see if you'll get anyone else to join, and I probably should make you. Oh, Amar is already a co-host, so I was able to set it up earlier. Hadassah, also a co-host. And hello, Umar. Nice seeing you connected. And you're also co-host. Okay. Let me zoom in just in case. It's too much out. Okay. So if you see anyone joining, please help me by accepting any visitors. Thank you. And since this semester is special and it's not always possible for all of us to visit all the meetings, I will repeat most important things, which will deal not with the academic part, but with the assignments, because in couple of not couple of hours, but in day and few hours, we will have one of our most important activities, and I know that it is a quite short notice and squeeze time. So we do need to provide what it is. Yeah, so you're doing projects. It is either a combination of two entities and exploration how the electronic structure responds to elevated temperatures, how it is changed, or one combines all these computational results into figures and tables. But in addition to figures and tables, there is one more thing that was not announced originally. So please add to your Word document with figures and tables a couple of pages of explanations what you did. So the goal of this written explanations is to mimic a true scientific paper. So the deadline announced here on the top page, I think, stays correct. So 5 p.m. tomorrow, but please come in person, even if typically you prefer be on Zoom, and please bring 3 printed copies. So if you want just to confirm with me in before, you can send me version by email, but I still need printed versions brought in the class, because there will be activity related to reviews of your write-ups. And let me give some suggestions on the writing if you haven't started, or if you started but get stuck. If you were watching recordings from yesterday, you will see an overlap, but since it is the next 5 slides differ from subject of computational chemistry, but it is critically important to complete the course requirements. And although it is less scientific, I need to repeat it, so making sure that everyone is on the same page. So we are not the first people in the human history who are trying to do scientific and non-scientific communication to an audience. In any part of the world, in any branches of human civilization, there were pioneers in this activity. And I'm just giving examples and accents on Roman and Greek civilization, but it doesn't mean that it is something exceptional or unique. The principles are the same. So in Greek civilization, it was basically just reflection what is going on, and focusing on things like design, what to communicate, design in which style. Most important, as we see from later, is how to logically arrange all materials so that they are digested best by the audience. And then a couple of other things, how to deliver and how to memorize, is maybe less important with our computerized PowerPoint and Word styles. So let me ask if any of you was taking Latin in the past in your education. Hadassah, no. Amara?
No.
No. Umar?
No, professor.
Okay, yeah, it's not required. It is humanities. It's not science. Haley, you are our last resort. Did you took any Latin in your previous education?
Unfortunately, no.
Okay, then we will just share, because you know as much as I do about this language, so we are on the equal foot. So let's just, in the order as you appear, I will ask you to help me to pronounce. So Hadassah, would you please read the first? Oh, read all three in the first row as you see them, to your best.
Delectare, docere, movere.
Okay, your pronunciation of Latin is better than mine.
I'm just going off of Spanish, but
Okay, yeah, they are of the same root. So is the translation on the second line looks adequate? So by scientific or non-scientific, by communicating some condensed amount of information to an audience, there are typically there are three goals: to please audience, because if audience is not pleased, they will just stop listening; to provide some new information, because humans by nature are curious; and to urge, to motivate audience to do something. These ideas of communicating between people, more formal communications, were designed like several thousand years ago, and examples how to motivate people to do something. For example, a military leader like wants his army to be more energetic while making a campaign, or an attorney wants to convince judge to make decision in favor of his client, or a salesman tries to like make you to buy something. Or in our case, a scientist wants to convince editor and reviewers to accept his or her paper, or government manager to fund grant proposal. So the component of motivating is always there, even if we do not realize it. So the most practical compared to Greek approach was Roman approach, and one of the examples is Cicero. You see here a little sculpture. So the ideas that I just shamelessly borrowed from the Wikipedia are designed several thousand years ago, but modern scientists project these principles on the way how the scientific papers are written. So by looking on this sometimes awkward, sometimes funny ways how to arrange elements of writing to audience can be helpful in making our own reports in the course. Okay, so Hadassah already practiced Latin. Next is Amara. Amara, would you please read the first word in blue?
Exordium.
Okay, yeah, thank you. So to Hadassah can make corrections if the translation to English is not exact or far from meaning, but to what Wikipedia tells, this word means arch forward, and it corresponds to an abstract in modern scientific papers. So it summarizes main reason for reader to continue looking on the poster, reading the paper, listening to the talk, and it summarizes the main finding, but in the pleasant, funny form, maybe giving a motivation who is getting benefit. So something that is short enough, but can keep audience to watch the rest of the, or read the rest of the material. Umar, would you please read the second word in blue?
Is it like narratio or narrative?
Okay, yeah, thank you. So it looks like English narrative, right? So like story. This corresponds to maybe the first part of the introduction section of modern scientific papers, where one tells, are we the first who is looking on a certain problem, or we are staying on the shoulders of giants, and any other thinkers were addressing similar problem in the past. So giving credit to others, giving basic background knowledge, explaining the context. So who is next? Let me check. The next is Haley. Haley, would you please read the third word in blue?
Maybe partitio.
Okay, yeah, thank you. So it also, I think, can be understood as by English analog. So divide by parts. So in modern scientific literature, it's like a table of contents or a brief summary at the bottom of the introduction, or it also overlaps with methods section. So in this partitio part, one summarizes the tools, the logical arrangement that one would use to discuss, to logically go through the materials. Hello, Lola. Nice seeing you connected. I think you were on the meeting yesterday, so it will be just hopefully pleasant memories about yesterday meeting.
Okay.
Okay. The Okay, since Lola is here, may I ask you to read in Latin once again? So would you please the line number, word number 4 in blue?
Confirmatio.
Yeah, so it also looks reasonable, like English to confirm. So typically, as if in scientific literature, we have some objective data, and this objective data serve as a reason to prove the case. Or, oh, I think Haley has the best vision of this. So if one goes through a court trial, it is like evidences that are provided by prosecutor or attorney to the court to prove the point that he or she is proving. Does it make sense? Haley?
Yeah, that makes sense.
Oh, okay, yeah, thank you. And in our scientific literature, it's basically a results section that logically overviews your evidences, your figures and tables, and tells how much they contribute to prove your point of view, your major statement that you want to prove. Okay, now let's go to the next round. Hadassah, would you please read the 5th word in blue?
Confutatio.
Okay, and what would it correspond to in Spanish? Is there any direct translation?
There's a similar. I'm not sure offhand.
But it's
Maybe like I'm thinking of the English word confound or to conflict with confutar. I don't know.
okay. Yeah. It goes really well. So some disagreement, treating the disagreement. I also do not have direct translation. So this is very important point that many scientists, especially those who just start their career, completely forget. And right now we are going to inherit wisdom of ancient thinkers and fuel our success in science. So this paragraph, this idea is really helpful. So what it tells that as an author or speaker or author of whatever video blog message, you are instructed by ancient thinkers to recognize that at least a half of the audience will disagree with you. So even if you did everything correctly, if you're absolutely sure that your theorems are proved, you have absolutely valid data, just by human nature, there will be people who by open heart will disagree because they do not find your arguments sufficient, or just by maybe some selfish reason they do not want to agree because their results are different. It doesn't matter why, but there will be someone who disagrees. And if you as an author recognize this idea, you may think ahead, what in my presentation, what in my writing, which of my statements will be opposed by readers, reviewers, and listeners. And by thinking this way, you may prepare your counter arguments, how to disarm your those who criticize you, what to answer if you will be criticized. So it's an additional thinking exercise to look forward, or maybe to try to criticize your own work and then try to defend it. So if you develop, or if you have already developed this skill, it boosts success of your scientific papers and grant proposals like at least 10 times. So it is a critically important part, because beginners typically just deliver fact material or share their excitement, and it's hard to believe that someone will not believe me, right? So if you admit an idea that someone will not believe you, you will be well prepared. Okay, and Amara, would you read the last word in blue?
Beta ratio.
Okay, so it's something per mouse, so some summary, and this little quote that I took from Wikipedia looks a little funny. So it's summarize arguments and then induce negative emotions to anyone who is against you, and induce positive emotion towards your case, towards you as an author, or towards your client. I'm not sure if we can be so literal in scientific papers, because it should be objective, but you have this idea what people were doing in ancient times. So how do these things project into modern scientific writing, and what one should write in the introduction? I'm sure that since you have selected your research direction, you know really well why you did it and what is your motivation. And here I'm going to just repeat to give a very brief and very silly example just of a style of thinking, how to motivate audience to follow you. This, so I apologize for being too simple and too silly, but even in the closed audience where we all are classmates, our projects are quite diverse. And if you want to convince a neighbor on the next desk that my project is interesting, I need to show who is getting benefit, why the project that I'm doing is useful to someone. So here is a little, I would say, oversimplified style of thinking. So suppose we are doing some science research. So the outcome of research goes into publications and patents. So like we discover new materials or new properties or new features that can be useful for industry. So this new, for example, new materials are used in the industry, and they are forwarded to generate energy more efficiently with less expense, or make new tools that serve, or maybe design new drugs, or increase security, and this all benefits simple citizens. But while looking on your own project, you may follow this line in more details to explain it. And as a feedback, happy citizens pay taxes to federal government, and federal government supports research. There is another way of this feedback. So at institutions like our universities, there is a generation of workforce who, like skilled research and developer people who also go into industry and contribute to this production cycles, or there are teachers who will teach next generation of researchers who provide general education to general citizen, and it also forms a feedback. It is quite oversimplified. Oh, hello, Hanmant. Nice seeing you connected. So I think you already saw this little slides. So I'm not telling that it is perfect or great. It just gives you general direction what to say in the introduction. Okay, how do we project these things towards our term papers in class? So if you haven't starting putting them together, even if you already have all your evidences, your figures and tables, it's like only one day until it is due. So one cannot write a lot even if you are talented and skilled writer. So it's one needs to identify most important things and try to communicate them clearly. So in the plan for written reports, we are inheriting part of the wisdom of this ancient speakers. And the first, we can skip abstract if the paper is very short, and we can include this exordium into introduction. So basically, an introduction should tell why his system is interesting, and if you are reading the literature, it's a good point to give reference. One may identify an open problem to formulate a scientific question that you are trying to address by your research. And since you selected by your problem, by your free will, you probably know the answer and you know the question which you wanted to address. Now, a little small but important thing. Formally, the answer to your question is expected to be provided in results discussion or in the conclusions. But to help digestion, how readers will digest your reading, right after a question, you can provide hypothetic answer to tell on your common sense analysis what is likely to be the answer to your question. So we are not going to make an intrigue and keep readers thrilled to wait until last page. We can give the answer later. Same as people do in calculus when introducing theorems. So one first formulates theorem and then provides the proof. So formulate the hypothetical answer. And this idea of question and hypothetical answer is very much appreciated by such agency as National Science Foundation. So later on, if in your career you will write grant proposals, it is the style you want to keep. And then at the end of introduction, you can express the hope that this computation by certain methods is expected to prove this hypothetical answer right or wrong. Okay, next section is methods. It's just help anyone who reads to reproduce your results. And it is a right way to provide maybe Kohn-Sham equations for like orbitals or anything that you use to compute and plot your observables, like formula for absorption spectrum. And please send me a reminder if you need a template. I believe I have some templates of this method section from previous years that you can use as a little inspiration. So send me emails after the meeting. Now, results and discussion. Basically, you write a couple of sentences about each figure. So going figures in the name, in the order they are numbered, explain what is computed, what is shown, and explain why the results look this way. And if they contribute to answer the question. And then in conclusions, tell if you believe that your evidences supported your hypothetical answer, and add any arguments why reader must believe you. If you can add like 2 up to 10 references, it's good, but in a given time frame, it might be not possible. So this is the main task. I'm going to tell more things today, but they are very secondary. So if your time is limited, you can just start writing right now if you haven't. And bring 3 printed copies tomorrow. Yeah. Confutatio discussion. Just realize that people sometimes disagree. Okay, so right now we have a little time, and I'm going to try and entertain you with more academic materials, but again, it is much more secondary in relation and comparison to completion of your written reports. So we, in this chapter, in the last month, we are focusing on the absorption spectra and methods to compute them. So in what we do in our practical mini research effort, we use picture of independent orbitals approximations, and the absorption is computed as combination of peaks maximized at transition energy when there is a resonance condition between incident light and transition between pairs of orbitals, right? And the height of the peak is proportional to so-called oscillator strength. And then we make summation of occupied and unoccupied. The time-dependent function density functional theory gives, it is designed to give same observable, but it uses quite different algorithm. Basically, it includes interaction between electron that has been excited from valence to conduction band and hole that remains in the valence band. Yeah, and transition dipole is just absolute value square of transition oscillator strength is square of transition dipole and some constants. So the major conceptual difference between orbital picture and the picture used in TDDFT and several other excited states methods, that when we do have orbitals like occupied, and here unoccupied, we are looking, each optical transition connects occupied and unoccupied orbitals. So we have two indices. In the excited state theories, we typically have ground state, which means everything below Fermi energy is occupied, not to G, ground or zero. And then we have excited states. So the first excited state is approximately corresponding to transition from HOMO to LUMO. So lowest excitation is from highest occupied to lowest unoccupied, and it will give the lowest excited state, but it is excited state number one, only one index. And then if we keep scanning different pairs of orbitals, we will have larger and larger transition energies. So it's, instead of pairs of indices, one use only one index for excited state. And then the goal is to find these energies and find oscillator strengths for probability to excite those states. The equation that provides answer to this question is based on discussion that we had in previous week. So it deals with transition density components, which are summarized in this X and Y. So transition density matrix is written in the vector form. Then there is a super operator that I hope to show in the next slide. And it is an eigenvalue problem. So we have operator times vector and the number times vector. So this vector is transition density matrix, which becomes non-zero only if system experiencing transitions from ground to excited. And these transitions may happen, they come into resonance to excitation frequency of the laser of light only at certain frequencies. So this is eigenvalue problem similar to Schrödinger equation or Kohn-Sham equation, but now we are finding not orbitals and their energies, but transitions and transition densities. So it's linear response theory. Just for curiosity, what are the components A and B in this eigenvalue problem? So I'm also repeating some, it's a revision of what was offered yesterday. In case we do not have interaction between electrons and electrons, holes and holes, and electrons and holes, if there are only independent orbitals, then the operator B, superoperator will be 0, and operator A will have only one term corresponding to energy differences between occupied and unoccupied orbitals. And in absence of interaction, electron-electron interaction, TDDFT will provide results identical to independent orbital approximation that we are using in our term project. The top 1, 2, 3, 4 lines correspond to predecessor of the TDDFT. So it is TD, time-dependent Hartree-Fock theory, and terms that correspond to interaction between electrons and holes are computed as anti-symmetrized Coulomb interaction. So one uses the indices used here and constructs this 4-orbital construction with a Coulomb kernel. So the stronger they interact, the stronger is this contribution. And basically by including these terms with this round bracket abbreviations, one takes into account corrections to optical transitions and to transition density matrices originating from interaction between electrons and holes. So it is this correction for some systems can be important, for some it is negligible, and one can discuss it. But our goal is not the TDHF, but TDDFT, which tries to avoid orbitals as much as possible. So instead of explicit Coulomb kernel, TDDFT uses the second derivative of total energy or exchange correlation contribution to total energy in respect to density. So when we are using the when we are practicing regular DFT, it includes the first functional derivative of total energy in respect to density, energy in respect to density. When we are using TDDFT, it includes second functional derivative. Okay. Now something new in respect to what was done yesterday. So suppose we have solved this Cassida equation. Suppose we have numerical data. Suppose we have certain transition, and for this transition we have transition density matrix. So we can tell that transition density matrix is total density in this at the time when system experiencing transition minus total density before light was switched on. So what is the difference between ground state and dynamic excited state density? When we were discussing these concepts a week ago, we were formulating a little snapshot of the transition density matrix that includes 2 orbitals below Fermi energies and 2 orbitals above Fermi energy. Right now, because the concepts are a little more complicated, I suggest we oversimplify it and look only on the green block near the homoluma. So we should recognize and realize that transition densities are, or transition density matrices are matrices. They have many elements. But right now, only for an example, our transition density X and Y will be represented only by one element, X and Y. So let's assume that for a certain transition, we do know this transition density matrices. And our goal is to follow a procedure how to compute oscillator strengths. So I'm providing an oversimplified example, and on this example, we will try to follow a procedure to compute oscillator strengths. Let me ask you to vote if this formulation makes sense. Hadassah? Amara? Umar? Okay, yeah, thank you. So here is the whole story in one slide. And I do have the same slide diluted into about 5 or 6 slides with going over it slowly. So let me overview and summarize what it is here. But if it looks too busy, do not panic, do not worry. I'm going to go over all details slowly but surely. Okay. Let's assume that you all got basic training in quantum mechanics and quantum theory, or you have heard a little bit of it. One of the concepts, one of the postulates of the quantum theory, of the quantum mechanics, and do not be scared of, I'm going to say something very simple and logical. So one of the principles is that quantum mechanics helps us to predict or to compute observables, to predict expectation values, observables that one can measure on an experiment. In order to know, in order to find an observable, one needs to know the wave function of a system, and one needs to know the operator corresponding to observable. And then expectation value that can be compared to experiment is computed as this convolution, the integral of the wave function conjugated, operator of an observable, and wave function. When we are doing independent orbitals approximation in our term project for optical properties, we are using this prescription. Since we are computing transitions, instead of expectation values, we are doing matrix elements. So we are starting initial orbital, for example, HOMO, final orbital, for example, LUMO. Then we have the elementary charge E times operator R position, which is a dipole dr integral, and then we get the dipole HOMO LUMO, right? Please confirm if you agree that it is what we do in our projects. Transition dipole is a matrix element of dipole operator in terms of Kohn-Sham orbitals. Okay, so it was not very confident, but yes, okay, thank you, Hadassah, thank you, Amara, thank you, Umar. Let me thank you, Haley. Lola, would you confirm? Or you want more explanations? Okay, let's assume that no request for explanations means agreement. Okay, now, when we are using TDDFT, we do not have orbitals anymore. We do have only transition densities. So we need to translate our prescription to compute expectation values from the language of regular quantum mechanics with wave functions to a language of density metrics. And on the language of density metrics, I'm going to postulate this equation and not going to prove it, although it is possible. So on the language of density metrics, expectation value is computed as so-called trace operation of a product between density metrics and operator. So if anyone needs a proof, just send me an email. I'll do it. Just want to save time right now. So the proof is just less than 1 page. So we are going to practice this prescription of finding expectation values for finding transition densities and oscillator strengths. So since we need to find dipole, we are going to make a trace of a dipole operator and transition density matrix. Right now, our transition dipole operator should be of the same dimensionality as density matrix. Our density matrix was chosen just to make everything doable in one page, in one slide, as a little segment, 2 by 2 segment near that includes HOMO and LUMA. So the dipole operator has zeros on the main diagonal and non-zero values on the subdiagonal, because transition dipole gives contribution only for transitions, as follows from the title. So static dipole has elements on the diagonal. Transition dipole has only off-diagonal elements. So please confirm if the statements in this line that I'm trying to highlight make sense, or at least if you are not going to protest against it. So please confirm. Okay, yeah, thank you. Lola, if you protest, please speak. If you agree, just do not show anything. Okay, yeah, thank you. Okay, and the next things are self-evident, but I think it is too busy and I better flip the slide. It will have the same information, just in more diluted form. Yeah, so trace of density times operator. So the operation of trace is just making summation along the main diagonal. So for 2 by 2 matrix A, B, C, D, it is A plus D. For now, we need to do a little exercise of multiplying 2 matrices. So I multiply the matrix for the dipole and a matrix for the density, right? So we're using rule of row by column. So 0 times row ho plus D times row lu ho will be D times row lu ho, right? Please confirm so that makes sense. If no, okay, yeah. If no, stop me anytime. I would be happy. Now, next element. So we do again 0D, 0 times rho ho. No, rho by column this 0 times rho ho lu times plus D times rho lulu. So we have this element D times rho lulu. Yes. Thank you, Umar. Thank you. Yeah. Thank you, Marath. Oh, Umar voted twice. Thank you. And the rest will be row d times row ho ho and d times row ho lu. So we did compute product of two matrices, but according to rules of quantum mechanics, in order to get the expectation value, we need to take only diagonal elements and add them together. So I take only things in the black boxes. So d times lu ho plus d times rho ho lu. And this will be the matrix, or either expectation value or matrix element of the transition dipole. So the elements lu ho and ho lu correspond to what is referred to as x and y in indentation of TDDFT, of density functional theory. And this x and y elements, they do depend on frequency, or they do depend on the index of the eigenstate, so the eigenvalues. And here, this little example shows us that if we have found transition density matrix element for a given transition number I capital, then we immediately have the transition dipole element. So knowledge of transition density matrix gives us transition dipole. Please confirm if it makes sense. Transition density gives transition dipole. Okay. This was, many thanks for confirming. This idea was the main goal of today's lecture. I will maybe show a few slides and speak a little bit more, but it was the main thing. So if you solve Cassidy equation, we have transition energies and we know transition densities, and transition densities help us to compute the dipoles. So X and Y density transition dipole. And then we can take absolute value of the transition dipole squared, put all needed constants like this 4, 3 pi for average over space, mass, electron, charge, elementary charge, and frequency. And then this will give us oscillator strength. So oscillator strength and transition energy or transition frequency is what we need to compute the spectrum, the absorption spectrum. So by today's little exercise, we did show how solution of Cassidy equation gives us all necessary information to predict spectra. I admit we were not deriving Cassidy equation. It should be provided with more details, but we made main effort to get an idea what to do with numerical solution of this equation. So it uses, the TDDFT uses different concepts to compute the same observable. And instead of pair of indices for transition energy and for oscillator strength, it uses one super index. Let me see if I have better summary. Okay, yes. So here we do have the comparison of the absorption spectrum computed in orbital picture on the left and excitonic picture on the right. So in the orbital picture, we have pairs of orbitals, and that determine us the energy of sets, transition energies, and oscillator strengths. In excitonic picture, we have one super index, uppercase I, which gives us transition energies, eigenvalues of Cassidy equation, and values of oscillator strengths that are computed from transition density matrix. Let me check if this little graphical summary makes sense and everyone can support it. Okay, yeah, thank you. Thank you very much. Okay, and let me see if you have more time. We are about to finish. Let me just give an announcement what we will be doing on Monday. So on Monday, I'm going to show examples of how one can run TDD, time-dependent density functional theory on Gaussian, and how to analyze the output. Ideally, I would do it in the lab and put analysis of papers in the lecture, but analysis of paper is more important, and the only time when we can meet together is Wednesday. So I'm sacrificing and moving this example to Monday, but I'll show as much as possible. So to run Gaussian, one needs to add keyword TD at the top of Gaussian, use like singlets, keyword root. And when one is looking into the .log file, it will give as an output the excited states, providing for each excited state the transition energy and oscillator strength. And when we meet on Monday, we will go into analyzing what other data are. Okay, I think it is more than enough for today. Many thanks for contributing to discussion and approving these little steps. Meeting is done. Everyone is welcome to disconnect. I'll stay here to answer any question, and wishing you a lot of luck and energy to complete your term papers by tomorrow. It's maybe most important or second most important there of equal meaning with the final presentation. So paper and presentation are just a top peak of our class activity. So meeting is done. Everyone is welcome to disconnect, and I'll answer questions if any.
Yeah. Go ahead, Amara.
No, you can do first.
Or my question could be a little lengthy. It's about my research. But, so go ahead.
So Professor, I have some issue about the, can I share my screen?
Oh yes, let me make you co-host. Just a second. Amara, you're co-host. You can share a screen. Yes.
Okay. So I am facing that issue when I try to plot the graph. Empty variance, I've changed the energy value, but it gets the same.
Wait. Can you type just in here, type more space states. More space states. Enter. Okay. Very interesting. First, I observe that you are using TDD, the Fairview. You're likely using excited states, right?
Yes.
Okay, this is cool. A second thing, I observe that your range of energies goes from maybe minus, it should go from minus 72 to plus 68 to minus 68. Let's scroll and see if it is what you request. So minimal energy here, you show from minus 20 to 0, right?
Okay, yes.
But it is wrong. You need to select these two, minimal energy and maximal energy, like maybe something in the vicinity of your homolumus. So minimal energy minus 72, maximal minus 68.
Okay.
To cover this range.
Okay.
Okay. And then it will generate data as needed.
Okay. I tried with -70, but I take maximum like 0. So maybe that's why.
No, you do not need to go to 0. And again, in most of the chemistry and material science, we do not have experiments unless you are doing X-ray. We do not have experiments that use energies more than like 3-4 electron volts.
Mm.
So therefore, we need only like range of few electron volts below and above HOMO LUMO. So this -20 plus 20 0, when your energy offset is several tens of electron volts, it needs specialized experiments that we are not going to describe. So if you use like battery with element with like that we are using in our home devices, is 1.5 volts. So it's not enough energy to promote electrons higher up.
Okay. Okay.
Okay. Was it all? Or there are other questions?
No, that's all. Thank you.
Okay. Yeah. Thank you. Okay, Hadassah, do you need to share screen or it will be a verbal question? Your microphone was muted.
Yeah. I guess I had a question. I was showing Andre the molecular dynamics stimulation or simulations or the heating process, and then he asked, or I just went with like 2,500 Kelvin because that's what we did in an example in class, and he asked like what the objective was of heating and doing the molecular dynamics of the system, because he suggested that maybe I was looking at it and wanted to look at an annealing process or something, but I guess for the scope of the project, what could I say I see from heating the system up?
Okay, I see your question or his question. The goal was not annealing, although it could be used for annealing. We do want, everyone here in class, we do want to make a little demonstration with limited resources. Like we have access to powerful computational tool, but we are limited in time. Therefore, we cannot do everything. And typically for these systems, one needs to make molecular dynamics at room temperature at 300 Kelvin. Make sense?
Mhm.
And at 300 Kelvin, there is a very humble and moderate molecular dynamics, which slightly perturbs, slightly induces a little coupling between electronic and nuclear degrees of freedom. So the main goal for the future continuation of this project is to compute non-adiabatic coupling, to see how electron can jump from one orbital to another one. But the room temperature gives a very, it would be more correct, but it will give very small effect. And for educational purposes, we are exaggerating temperature just to see very exaggerated effect of nuclear motion on electronic structure. So that to convince everyone in class that if ions move, it dramatically modifies electronic structure.
Mhm.
And with these settings of 2000 Kelvin, it will be definitely a very big change. Sometimes non-realistic, sometimes not relevant, but it is something we can do within a week and complete our project and our activities in class.
Okay.
There is another comment. So we, with Professor Krzyzewski, your advisor, we are at the same time friends and collaborators, and we at the same time we are competing in the ways to compute electron-phonon coupling. So we are defending in front of each other different methods. And probably you will be learning his method to more extent. And the method that I'm offering will be only for information. And neither of us is designer, we just selected this method. So his method of computing that method that he likes for computing electron-phonon coupling is based on exploring normal modes, exploring the eigenfrequency of phonons. And after this eigenfrequencies of phonons are known, he is displacing all system along this normal mode coordinate and looks for response of electronic structure to displacements along normal modes. Make sense?
Mhm.
This is a very cool method, and it is especially good close to 0 Kelvin if the amplitude of nuclear motion is small, if everything is harmonic. The method that I am adopting, again, I'm not the designer, just find it useful, does work for very non-harmonic potential energy surfaces. So instead of looking for displacement along this harmonic normal modes, I suggest that we look for molecular dynamics which explore system in all points of phase space. And then as we go from point to point, we just make same derivatives in respect to change of nuclear position and compute electron-phonon couplings. So in certain limits, these two approaches will give same results in the limit of low temperature and small amplitude of nuclear motion. But in the higher temperature regime, the molecular dynamics approach is more universal because it includes naturally any possible unharmonicity and even bond breaking, while normal mode analysis is limited. And it's with Professor Krzyzewski and myself, it is our favorite entertainment to start to argue and about these two methods, and each of us defend one or another. And I think you're getting slowly involved into this discussion. So
Okay.
yeah, by some reason he's not very excited about molecular dynamics, and he's trying to oppose it.
Okay.
just so you know. And after you finish the course, nothing will hold you to do it if you do not like it yourself. But for the course, let's do it.
Okay. Yeah, I mean, I already have the videos made. I was just, while I'm preparing my report, I'd like to comment on these are the molecular dynamics videos. This is why they're important for this. And yeah.
Okay. Yeah. Thank you for the question and for discussion. I think it's good that we are on the same page and have some understanding of what is going on.
Okay. Thank you.
Thank you. Are there more questions or that's it?
No, that's it.
Okay. Yeah. Have a nice day.
You too. Bye.
You too, bye.